Okay. Alright, so just the first part. I'll just do the first part first. So use geometric element to explain why z minus 1 on z plus 1 is purely imaginary. So z minus 1 is that vector there. So that's z minus 1. And z plus 1 is this one here. So that's that vector there. So z's moving. Okay, so z's moving. You can see it's here's z, here z's on that unit circle there. I'll just redraw that. Now on a circle, the angle on a semicircle is a right angle. So if you did the argument of z minus z1, and you can show that it equals 90 degrees, then if its argument is 90 degrees, that means that it will lie on the y-axis, which makes it purely imaginary. Okay, so take the argument of z1 on z plus 1, and that will equal the argument of z minus 1 minus argument of z plus 1. So if you look at this argument here, we're talking about this angle here, which is, we'll call that alpha, and this angle here, which we'll call that beta. Now alpha minus beta, what is that actually equal to? So that is a right angle triangle there. So if we call that A, B, C, so the angle sum of triangle A, B, C equals 180. So that means that, if we look at the exterior angle of the triangle rule, alpha plus 90 equals beta. So this one in here is alpha, this one here is beta. So beta plus 90 equals alpha, so 90 will equal alpha minus beta. That's because the exterior angle of a triangle. So therefore, the argument of this will be equal to 90, which makes it purely imaginary because it will lie on the y-axis. Okay, now if you look at the second part, so the second part show that, and similar result for sine, and I think you can do that pretty easy because we've got, so you've got e to the I theta plus e to the minus I theta with a half. So it's just a half sine cos theta plus I sine theta. And for the negative one, it is cos theta minus I sine theta, because that's going to be minus theta, and cos of minus theta is cos theta, and that one's sine of minus theta, which is minus sine theta. So the sines go out, and you get 2 coses times the half, so that's why that equals cos theta. The sine result will be, it is equal to a half e I theta minus e to the minus I theta. When you simplify that, you'll get the same thing. That will be the sine result. Okay, so use the result from part 2, so specifically want to use that there, to show that z minus 1 on z plus 1 equals I tan theta on 2. Okay, now because we've got the I tan theta on 2 there, okay, for the third part, maybe I didn't actually realise it said using part 2. I've been going from this side and getting to that way. So if I want to use part 2, then potentially what you would be doing is using that and trying to get the z. Because part 2 has this expression for the trig function. So if you had sine theta on 2 and you made that on cos theta on 2, then you could use the e's to do that. So that's a half e to the I theta plus e to the minus, because that's this, I want minus because it's sine, minus e to the minus theta. And then on the bottom, I want a half e to the I theta plus e to the minus I theta. Now, the halves will go out. You've got e to the I theta minus 1 on e to the I theta over e to the I theta plus 1 on e to the I theta. So if you get that and you multiply top and bottom by e to the I theta, you end up with I times e. Actually, it's not theta that should be in there, it should be theta on 2. Theta on 2, because this was sine theta on 2. These are all on 2. All on 2. So if you multiply by e to the I theta on 2, e to the I theta on 2, that will get rid of like the denominator there. So you have e to the I theta. So you have e to the I theta times e to the I theta on 2. E to the I theta on 2 times e to the I theta on 2, which will give you e to the I theta on 2 plus theta on 2, which gives you e to the theta minus 1. And on the bottom, so that will be e to the I theta as well, because it's going to be I theta on 2 times I theta on 2, which is I theta on 2 plus I theta on 2, which gives you I theta. And then on the bottom, it's going to be plus 1. So really what's happening when I multiply the top and the bottom, just to make this really clear, so you get e to the I theta on 2 minus 1 over e to the I theta on 2, all over e to the I theta on 2 plus 1 over e to the I theta on 2. So when you have that and you multiply the top and the bottom, because that comes from I tan theta on 2, which is I sine theta on 2 on cos theta on 2, and that's what I've got here. Now, they did have a half, but the half would have cancelled. So if I multiply this by I theta on 2 and that one by I theta on 2, then you'll get, when you multiply these two things together, you get e to the I theta on 2 plus I theta on 2 minus 1 over e to the I theta on 2 plus I theta on 2 plus 1, which gives you e to the I theta minus 1, e to the I theta plus 1. But e to the I theta is z, so it's z minus 1 over z plus 1. And that's how you could do it using the rule, which is what it said. Prior to that, what I've been doing is I change my, if I've got that there, I change my z to 2 theta. So, I've got cos theta plus I sine theta. I change the cos theta to cos squared minus sine squared, theta on 2. Cos squared minus sine squared theta on 2. And I change the sine to 2 sine theta on 2, cos theta on 2. Because by doing that, when I'm doing that, I'm basically breaking the thetas up to thetas on 2s to get my tan.